Hello everyone, I'm Izabela Horvath and I am presenting METGAN, Generative Tumor Inpainting and Modality Synthesis in Light Sheet Microscopy. The dataset that motivated this project highlights the metastatic spread of cancer through a mouse organism. An intriguing feature of this dataset is the multi-channel nature of the data. An autofluorescence channel images general tissue, and the pathology channel marks objects of interest such as tumors using fluorescent dyes. The goal of this application is to generate synthetic images in the pathology domain based on information in the anatomical channel with metastases placed in user-defined locations. In order to learn this task, we use existing annotations, which are very time-consuming to obtain and are often inconsistent or noisy. For example, this image from the lung area shows us that many micrometastases are missed in the annotation, even though some of them are very bright. Our first step was reviewing existing methods. However, our experiments showed us that these often fail to generate semantically correct images when underlying annotations used for training are noisy. Current image translation approaches, such as Pix-to-Pix CycleGAN or CIFA, perform image translation of structures that are visible in both domains. However, this is not the case in our application. Other approaches, such as Paetzold or RedGAN, generate images based on labels in the target domain. This leaves the generator with the task of synthesizing backgrounds that fail to take advantage of structurally rich priors. Our application, however, aims at carrying out image translation and semantic synthesis concurrently in a robust manner. As a general architecture, we propose a cycle-consistent 2D customized GAN whose layout is depicted in this figure. Our method uses two dual-channel generators that have separate inputs for the anatomy channel and the label. Features from the label are extracted through a pathway tailored for semantic synthesis using 7 spade ResNet blocks. These features are then fed into the upsampling layers of a unit architecture that receives as input the anatomical channel. The two generators are trained in a cycle-consistent manner with an additional pairwise loss in both domains. Generator F, whose task is to create synthetic images in the cancer domain, is further constrained by a pretrained segmentor whose weights are fixed. This helps ensure that the generated output is consistent with the desired label. Our final loss function is a parametric combination between discriminator, cycle, segmentation, and pairwise losses. We compare our method against state-of-the-art image translation and semantic synthesis networks. From the qualitative results, we can notice that networks originally created for domain adaptation fail at enforcing correct semantics or create unrealistic tumors. For example, Pix-to-Pix often tends to place extra metastases, while CycleGAN does not place them whatsoever. On the other hand, networks that specialize in semantic synthesis generate unrealistic images with mostly trivial backgrounds, losing the rich anatomical information that we have. In a quantitative comparison, our proposed method outperforms most state-of-the-art methods in mean absolute error, mean sum of square differences, image similarity index measure, and the learned perceptual patch similarity. In a further robustness study, we show that even at a rate of 25% incorrect labels, METGAN can still learn to generate semantically correct images in the target domain, unlike Pix-to-Pix or CycleGAN, which place random metastases as highlighted in this image. Lastly, we analyze how METGAN images can be used to augment real data for training segmentation networks. We successfully train segmentation models on sets of synthetic, real, or mixed data with a varying number of samples from each set. The range and mean of 5-fold cross-validation can be observed in this figure. We can see that synthetic data boosts performance and improves stability, especially in lower data regimes where training on real data becomes unstable. Moreover, we achieved the highest dye score using a combination of real and synthetic data. The detection is improved, particularly for smaller tumors, showing the fact that we can tune our generated samples to the main failures of the original network. In conclusion, we introduce METGAN, a novel generative method which is able to leverage real anatomical information to generate realistic image label pairs of tumors that are superior to other methods from a qualitative and quantitative point of view. We are able to carry out domain adaptation and semantic synthesis at the same time in a way that is robust to noisy labels. The generated data allows us to improve the segmentation performance on the downstream task and can be tuned for corner cases where the original segmentation network fails. Furthermore, we presume that this method can be extended to other imaging modalities, such as MRI, CT, or other types of microscopy to create contrast-enhanced label data. Thank you for your attention.